Hello students, let us come back to module number 4, sequential circuit. So sequential circuit module number 4 is very important module as far as examination point of view. Sequential circuits contain the basic building block, what we call it as a flip-flops. So in today's discussion we are going to explore the feature called as a flip-flop. Flip-flops are basically a single memory element which are used to construct a sequential circuit. So there is a big difference between sequential circuit and combinational circuit. Combinational circuit we saw the earlier module, multiplexers, decoders, demultiplexers, encoders, all these are the examples of combinational circuit. Then how the sequential circuits are different from combinational circuit. The case is, in sequential circuit, an extra element called as a memory element or the extra part of the circuit which is able to store some memory is involved in the construction of the circuit. So sequential circuit is essential a combinational circuit only, but in addition to that it involves the use of some kind of a memory element. So let us start making notes on sequential circuit module number 4. I hope my screen of iPad is visible to you. So we are starting with the module sequential circuit, module number 4 in the syllabus. So let me start over here. Module 4, sequential circuits. Sequential circuits. So what is the definition of sequential circuit? Sequential circuits are combinational circuits, right? Plus additionally they have the memory element. Additionally they have the memory element. Now this memory element can store single bit value, right? And this value could be either 0 or 1. Either 0 or 1. Okay. So this is very important in the case of sequential circuit. So we are talking about a sequential circuit. Sequential circuits is nothing but the combinational circuits only. Okay, so here I highlight that part. We saw earlier the different types of combinational circuits: multiplexer, demultiplexers, decoders, encoders, and so on. But along with that, what they contain is additional as a memory element. They do have memory element, and this memory element can store a single bit value, right? And this value could be either 0 or 1. So if we want to draw the block diagram of sequential circuit, how it look like? It look like simply the combination of combinational circuit and memory element. So let us draw it. So here what I will do is I will first make a box for combinational circuit. Okay, so here is a combinational circuit. Combinational circuit. But along with this, what it has is additional part as a memory element. Okay, it has additionally a memory element. Yes, so this is a memory element. So when you combine these together, in this way, and when you take some feedback from the memory element back to the combinational circuit in this way, this is a feedback, right? So the output of memory is again feedback to combinational circuit, and this combinational circuit has its own input separately. Okay, so in this way. So here this output is what we call it as a output of sequential circuit. Output of sequential circuit. So I hope you understood the basic difference between sequential circuit and combinational circuit. Okay, so sequential circuit is essentially a combinational circuit itself, but with one part added to it. Okay, so this is nothing but this memory element. Okay, I am highlighting this. So this is the additional part. This is the additional part. I hope my handwriting is visible to you and you can understand the handwriting. Okay, so few of the parts are highlighted. So this is the simple introduction to what we call it as a sequential circuit. So what is the example of sequential circuit then? The best example of the sequential circuit are flip-flops. Okay, so let us talk about flip-flop. I will start writing here flip-flops. So what are flip-flops? I will first write here the definition. Flip-flops are single memory elements, okay, used in the construction of sequential circuits. So this is the simple definition of flip-flop. So flip-flops are, in other words, you can say these are the basic building blocks of any sequential circuit. Okay, so there are 4 basic types of flip-flops mentioned in our syllabus. Okay, so today we are going to see the details of these different types of flip-flops. Okay, so the types of flip-flop. Let us explain the types of flip-flop. These flip-flops are slightly different from one another, and let us see characteristics of them, how they look like, design point of view, and the truth table and the circuit diagram. Types of flip-flop. Okay, basically 4 types of flip-flops we have. Number 1, we call it as a set reset flip-flop. Set reset flip-flop. Okay, set reset flip-flop, or in short we call it as a SR flip-flop. SR is the short name for the set reset flip-flop. Second is very popular, we call it as a JK flip-flop. Simply JK flip-flop. Third is D flip-flop. D, capital D flip-flop. D stands for data. D stands for data, or you can call it as a data flip-flop also. And fourth is T flip-flop, capital T. Okay, so T flip-flop is also called as a toggle flip-flop. So what is the meaning of toggle? Toggle means it changes the state one after the another rapidly. Okay, so for example, at this given moment of time, if the state of the flip-flop is 1, the next moment of time it will become 0, and the next moment it will become 1, and it will continue in this way. So that means the output of the flip-flop continues to toggle between 0 and 1. Such a kind of a flip-flop we call it as a toggle flip-flop, or simply T flip-flop. Okay, so one by one let us go into the details and explore the truth table, the working principle, and the state diagram. Okay, because we know that the flip-flop will be there in one particular state. From one particular state they will change to some other state. So state diagrams are very important characterization of the given flip-flop. So let us go one by one and see the details of these four basic types of flip-flops. So first of all, let me mention here, the first is set reset flip-flop. Set reset flip-flop. Okay, so how it look like? Okay, so first of all, let me draw a block diagram, simple block diagram. Set reset flip-flop, single flip-flop. Okay, okay, so this flip-flop has two inputs. One input we call it as a S, another input we call it as a R. Okay, and it has two outputs. The output is Q, and the another output is a complemented version of the original input, that is Q. So Q and Q dash, these are complements of each other. So where S and R, right? So these are inputs of flip-flop. These are inputs of flip-flop, and Q and Q dash, these are output of flip-flop. Okay, so additionally some other control signals can also be shown for the given block diagram of the flip-flop. For example, a clock signal. So this is a symbolic representation of a clock signal. Okay, so the clock could be positive edge triggered or it could be negative edge triggered. If we draw a bubble at the input of this particular triangle in this way here, this is called as negative edge triggered flip-flop. On the other hand, if you remove this bubble here, and simply if you connect a clock input by showing a triangular sign in this way, this is called positively triggered flip-flop. So in short, we write this as FF. FF stands for flip-flop. Okay, so in addition to the clock signal, two more control signals are popularly shown to any particular flip-flop. These two control signals we call it as a preset. These are active low signals. So this is preset. Okay, and another terminal is the clear terminal. So what is the job of these two extra terminals? Preset, these terminals are common for all different types of flip-flop. Preset is active low control input used to set the flip-flop. We will see what is the condition of setting of the flip-flop. Okay, so we will understand the term setting of the flip-flop later on. And what is the another terminal called as a CLR? CLR stands for clear terminal. So this is again active low control input. This is again active low control input. And for what purpose it is used? Used to clear the flip-flop. Whatever the memory, 1-bit memory that the flip-flop is going to store, if that memory, if you want to clear, then you can apply logic 0 at the input of CLR control pin, right? So being it is active low, when you apply 0, it will become inverted and it will become 1, and the clear terminal will be active, clear the flip-flop, and this will clear the contents of the flip-flop. Okay, so this is a common practice to show these two control signal inputs. Many of the times showing these two terminals, preset and clear, can be omitted for the sake of simplicity. Okay, and please remember there are two outputs, Q and Q bar. Okay, so I will highlight here. So Q and Q bar, these are the two highlight. So this is actual output and its complemented output Q bar. Okay, so this is a simple block diagram of SR flip-flop or set reset flip-flop. Okay, now let us write the truth table for this flip-flop. Okay, so truth table. So writing a truth table could be tricky for the given flip-flop. So please pay attention. So here there are two inputs are there for the given flip-flop, right? So S, I will write R here. Okay. Now what we'll do is we will represent the two output states of the flip-flop. One representing the present state, another representing the next state. Okay. So let us write here Q is representing the present state of flip-flop, right? And let us denote Q to the suffix plus. What it represents? Let us say it represents next state of the flip-flop or the future state of the flip-flop. Next state of flip-flop. Next state of flip-flop. Okay. Then let us write a truth table for this set reset flip-flop in terms of input S and R and in terms of output states. There are two output states, Q and Q plus. Okay. So we will write these Q and Q plus. Please remember Q is a present state and Q plus is the next state. Okay. So first of all, I will give, as there are two inputs. What are the two inputs? S and R, these are the two inputs. So how many combinations are possible? 4 combinations, 0, 0, 0, 1, 1, 0 and 1, 1. Let us write that first. So this is 0, 0, 0, 1, 1, 0, 1, 1. Now let us say for all these 4 different combinations of the input pin S and R or the input control signals S and R, the present state, that is Q, let us say it is 0 for all these 4 input combinations of control lines S and R. Then we would like to write what will be the next state, that is the truth table. Okay. So similarly we'll have 4 more conditions when we want to keep the present state of the flip-flop is equal to 1. So let me separate out this a bit differently so that we can distinguish the difference. Okay, so here I will draw a line with a red color. Okay, again what I will do is I will rewrite the S and R input. Okay, so 0, 0, 0, 1, 1, 0 and 1, 1. And now this time I want the present state of this set reset flip-flop, that is Q, to be 1. Okay. So 4 combinations. For all these 4 combinations, the present state we are considering Q as a 0. Similarly, again for the 4 different combinations of set reset control inputs, we will consider the present state as equal to 1. And for that we want to write what will be the next state for all these 8 different combinations, and that will give us the truth table for SR flip-flop. Okay. So when, let me write here, when the condition is 0, 0, the next state we want 0. So here the Q, the next state will become 0. Please remember this is a truth table for set reset flip-flop. So how to read? When set and reset both are 0, and when the present state is 0, the next state will become also 0. Okay. Now next, when the present state is 0 and the control second case goes from 0 to 1, so this particular condition indicates reset condition. Okay. So when R becomes 1, it will indicate reset condition. So still reset means present state is 0, next state is reset. Reset means it will again remain 0. Okay, so this is called reset condition. Let me write here. This is called reset condition. Okay. Now next, condition number 3, when S becomes 1 and R becomes 0. So this is called set condition. And when the present state is 0, the next state will become Q plus will become 1. Please remember. So this is called as a set condition, opposite to reset condition. Okay. And finally, the fourth state, when both control are held 1 and the present state is 0, please remember the next state is not expected, or this is a don't care condition. And please remember, in the case of set reset flip flop, making both the controls 1, that is set is equal to reset is equal to 1, is not allowed condition. Okay, so this I will write not allowed condition. So that's why the next state Q plus I wrote as don't care condition and indicated at cross mark. Okay. Similarly, let us write the fifth. When we consider the present state of the Q is 1, 0, 0, no condition change. Okay, so 0, 0, no condition change. So it will remain 1 only. Okay, it will remain 1 only. Next state will become 1 only. Now when the input S is equal to 0, 6 condition, and reset is equal to 1, and the output present state is 1, the next state it will become 0. So this is again a reset condition here. Reset condition. Right? Seventh condition, when it is 1 and 0, this is called as a set condition, and the output is 1 right now, and the output will remain 1 only. The output will remain 1 only, and this is called as a set condition. And again, for this particular combination of present state 1, if we keep both inputs both high, then the next condition is don't care condition, and this is not allowed. Okay, not allowed condition. Not allowed condition means what? We will not allow, or we will not consider the condition when both S and R equal to 1. So here, important thing I will write here, both S is equal to 1 and R is equal to 1 condition is invalid for SR flip flop. For SR flip flop, I will simply write as a FF. Okay, so let me highlight this part. This is very important. So what is the condition? When both S and R is equal to 1, this particular condition is not allowed in the case of set reset flip flop. Okay, while other conditions are absolutely okay. Okay, while other conditions are absolutely okay. Now this is the truth table. Now on the similar basis, how we can write the excitation table? Okay, so actually the truth table and excitation tables are one and the same. Okay, but there is a still difference, because excitation table is a sub part of the truth table, you can call it as. Okay, so let us write the excitation table. So see how we can write the excitation table. Okay, so let me highlight the excitation table here. Excitation table means what combinations you will select for S and R in order to get a particular present state and output state condition. Excitation table. So the excitation table is simple. So first of all, you need to write Q, that is the present state. So let me write here the present state. And next state, how we write Q plus, right? That is the next state. And then we need to choose the control S and R. So basically these are the inputs. Okay. So let us say your present state is 0 and the next state you also want it to be 0. Then what inputs S and R should be? So the standard inputs are S should be 0 and R is a don't care condition. Okay. So for this particular combination of S and R, when the present state is 0, the next state will again remain 0. Okay. Similarly, when the present state is 0 and when you want the next state to be 1, so this is a set condition, and whenever set condition is there, you need to make S is equal to 1 and R is equal to 0. Okay, this is a set condition. Next, what is the combination? Your present state is 1 and next state you want to make it 0, so this is actually a reset condition. For that case, S should be 0 and R should be 1. Okay, and the final condition, the present state is 1 and the next state is also 1. So for that you need not to change don't care condition for S, and R you need to keep it 0. Okay, so this is the excitation table of SR flip-flop. Okay, so let us draw the state transition diagram for this SR flip-flop. Okay, so please pay attention. So how to draw the state transition diagram for SR flip-flop. So here I will draw state diagram or state transition diagram for SR flip-flop. State transition diagram for SR flip-flop. Okay, so pay attention carefully how to draw the state state diagram. Okay, so first of all you need to take help of this SR input and present state and next state. Okay, or you can draw the state diagram with the help of truth table also. Okay, so let me draw here two states of the flip-flop. Okay, Q is the output, right? Q is the output. So here I will write this as Q is equal to 0. Okay, and in another circle, so what this circle represent? This circle, they represent the unique state of the flip-flop. Then another state would be Q is equal to 1. Okay, now refer to the truth table. Refer to the truth table. Okay, so let us consider that we are here in Q is equal to 0 state. We are here. Okay, so this I mark with a tick mark. Okay, we are here. Okay, now when S is equal to 0, when S is equal to 0 and R is equal to don't care condition, that means R can be either 0 or it can be 1. Okay, the next state will be 0. Okay, so how this can be shown? Okay, see, you can take the help of the truth table. Okay, so see the truth table. When S is equal to 0, R is equal to 0 and present state is 0. So right now Q is equal to 0. So S is equal to 0, R is equal to 0. The next state will be again 0 only. So that means we can show this in transition diagram in this way. So what is happening? What this arrow is indicating, that you are returning back to the Q is equal to 0 state only. And what this arrow represents? This arrow represents next state, Q plus. Okay, so Q plus is again 0 for what combination of S and R? This combination of S and R is equal to 0 and 0. Okay, then next, you are still here at Q is equal to 0, okay, and then you make S is equal to 0 and R is equal to 0. Again it will come to the same position, okay, that is next state will be again 0. The transition diagram, the transition arrow will be same, and now this time S and R is 0 and 1, okay. So this condition we saw now, right? Now next condition is you are here in the 0 state and you give the input S and R is equal to 1 and 0. What will happen? The flip-flop will change the state and it will become set. The next state will be 1. So that means it will make a transition from Q is equal to 0 to Q is equal to 1. So this arrow indicates transition, change in the state. When this will happen? This is a Q plus, that is the next state. So when Q is equal to 0, the next state is Q is equal to 1. This is indicated by Q plus, and this will happen when you make S and R equal to 1 and 0. Okay, so this we explained in third condition, right? Now when you make both equal to 1, right now you are here now, Q is equal to 1 on the second state. Now if you make both S and R is equal to 1, that is not allowed condition. That is not allowed condition. Okay. Now consider the fifth condition. So we'll not consider the fourth condition to be shown in the state diagram because it is not allowed. Okay. So let us directly go for the fifth condition. In fifth condition, you are here again at Q is equal to 0 on the left hand side state diagram. Okay. Now see here, Q is equal to 1. See here, condition the step number 5, Q is equal to 1. So here you are here now. Okay. Now Q is equal to 1, and when S and R both are equal to 0, what will happen? The next state will be again 1, right? So it will remain in that state only. So this you can show with this transition arrow diagram. This transition arrow diagram is showing or indicating next state. Next state will be again same, 1 coming back to 1, right? And this will happen when again when you keep S and R both equal to 0. Okay. Now when you make S and R 0 and 1, that is reset condition, 0 and 1. So what will happen? I am explaining the sixth step. Okay, so what will happen? The next state will become 0. So right now you are here at Q is equal to 1, and when you make S and R is equal to 0 and 1, it will come back to the Q is equal to 0 condition. So this will happen when the next state will become 0. From 1 to 0 it will go to 0, and this will happen for S and R when you keep 0 and 1. Okay. Now you are at Q is equal to 0. Okay. Now again consider when you are at Q is equal to 1. Let us say the seventh step, seventh case. Your Q is equal to 1 here, and when you make S and R is equal to 1 and 0, S and R become 1 and 0, it will again set the condition and it will come back to the same. So the next state is again shown, S and R, the same arrow you can use when making 1 and 0. S is equal to 1 and R is equal to 0. It will return to the same state, no change. Okay. And when you make again 1 1, that is not allowed condition. So this particular transition of the flip-flop state from one to another position shown diagrammatically with the arrow diagram, we call it as a state transition diagram or state diagram for the given SR flip-flop. Okay. Now let us write the equation for this SR flip-flop. Equation for this SR flip-flop. So let me write here. Again we are taking the help of truth table in order to generate the equation for SR flip-flop. Okay. So let me write here equation of SR flip-flop. equation of SR flip-flop. Okay, so how to start writing equation of SR flip-flop? So what we will do is, we will take the help of truth table. Okay, so in truth table we have 8 different possible combinations of input S, input R and present state Q of the flip-flop. Okay, so inputs, here I will write, inputs are S and R, and output we consider the present state. So what is the present state? How it is denoted? It is denoted by Q. So by taking these 3 inputs, that is S, R and Q, we want to write equation for next state, that is Q plus of flip-flop. Okay, so this we can easily do by looking at the prepared truth table already, and we can reduce this by using K-map. Okay, so we know that we have the 3 variables S, R and present state, that is Q. Okay, so we can construct a 3 variable K-map. We know that a 3 variable K-map will contain total 8 elements. Okay, so let us draw the K-map for 3 variable in order to generate equation of set reset flip-flop. Okay, so here I will write K-map for 3 variables. What are the variables here? The variables are S, R and Q, and we want to write equation for Q plus. Okay, so we already know how to draw the 3 variable K-map. Okay, so let me draw here the 3 variable K-map. Okay, so 1, 2, 3 and 4, and this is another one. Okay, so we can have the K-map like this. Okay, so what we do is S and R we take on this side, and Q we take on vertical side. So Q is equal to 0, Q is equal to 1. Now this is 0, 0, 0, 1, 1, 1 and 1, 0, right? Or you can write this as Q dash and Q, and similarly here you can write S dash R dash, S dash R, SR and SR dash respectively. Okay. Now what you do is you enter in this K-map, 3 variable K-map, wherever the Q plus output goes 1. Okay, and wherever it is don't care condition. Okay, so such a 3 conditions are available here. I will highlight those conditions here. Okay, with some, let's say, different color. Let me choose this green color. Okay, so see here, for this particular combination the output Q plus is 1, right? Similarly at another combination, say here, the output is 1, right? Q plus output is 1, and here it is 1. Okay. So for these 3 conditions, the K-map will contain the value is equal to 1, right? So 1, 0, 0, S, R, Q, 1, 0, 0 is 1. So let me choose S, R and Q. See here, S, R and Q, the highlighted third step, 1, 0, 0, 1. Output Q plus is 1, right? So here 1, 0, 0 is 1. I will make entry here 1. Okay. Next, where it is another 1, when the Q plus will become 1 for the 5th step, right? 0, 0, 1. So 0, 0, 1, that means here, right? Next, the 7th step. See the 7th step which I highlighted is as a set condition. 101, 101, again it is 1. Okay, so in this way. And as X are treated as a don't care condition, those don't care conditions are also included, and we can take advantage that we can treat them as a 1 and we'll use it for reducing the K-map. Okay, so what we'll do is I will highlight that and I will show it differently. What we'll do is we'll take this don't care condition also to be included in the K-map. Why we are doing so? We are doing it purposely because we can take advantage of this don't care condition and treat them as a 1. Ultimately, it will reduce the given expression for next step Q plus. Okay, so first X will come in step number 4, that is 110, S1, R1 and Q0, 110, 110, that means this particular position here I will mark it as a X. Okay, and another, the step number 8 here, right, 111, all are the 1, 111, all are the 1. Okay, rest of the things we can put as a 0. Okay, so what we want now, we want to, again we know the rule, we want to form a group. Okay, and we know the rules of forming a group while using a K-map. You can form a group of single elements, you can form a group of pairs, you can form a group of 4, and you can even form a group of 8 combinations. Okay, so what I will do is I will treat this don't care condition here as 1, and I can form a group of 4 elements together. This we call it as a quad. Okay, so for that let us write what are the expressions for each of these cells which forms this group. Okay, so for this the expression will be S R Q dash. Okay, and for this the expression will be S R dash Q dash, right? Similarly for this particular cell the expression will be S R Q, and similarly for this particular cell the expression will be S R dash Q dash. Sorry, this was 111, no? So it's a 111, yeah, 111, and sorry, this I made a mistake here. So this is 101. 101 means it's S R dash Q, right? S R dash Q. Okay. Now what will happen? Which terms will get cancelled out here? This is representing the whole group. Let me group it. In this way. So what will get cancelled here? So here R will get cancelled with R dash, R will get cancelled with R dash, right? Then this Q will get cancelled with Q dash, this Q dash will get cancelled with Q, and this will give you the term S, only S, right? Now another one is remaining here. So what you can do is you can fold the K map vertically in the middle direction. What you can do is you overlap this one, this element 1 with this element 1. Okay, so what is the expression for this? The expression for this particular term is S R dash Q. Okay, and for this it is S dash R dash Q. Okay, so who will get cancelled here? S dash will get cancelled, and the remaining term will remain as R dash Q. So this is the equation for the next state of the SR flip-flop. So here we can write next state. I will change the pencil. Let me choose this dark one. Next state how it is given? Q plus is equal to, now this is S plus R dash Q. S plus R dash Q. So this is very important. Next step, equation of the SR flip-flop is given by this particular equation. Q plus indicates next state. Okay. So this is all about the first flip-flop, that is set reset flip-flop. Okay. So the block diagram, the truth table, excitation table, the state diagram, and the equation, and we derived the equation by means of taking help of K-map reduction technique. Okay. Now this is all about set reset flip-flop. Now similarly, let us go for the next flip-flop, that is JK flip-flop. Okay. JK flip-flop is similar to SR flip-flop, but the only difference between the JK flip-flop and SR flip-flop is that we saw in the case of SR flip-flop, the two control terminals S and R both are not allowed to become simultaneously one. Okay, but this is not the case with the JK flip-flop. The both terminals of the JK flip-flop, that is J and K terminal, they can become one at a time simultaneously, and this is what it is advantageous over here in the case of JK flip-flop. So let us have a detail of JK flip-flop. So let me start writing here. Second flip-flop, JK flip-flop. Okay. Now quickly let me draw the diagram, block diagram. Okay. Block diagram of JK flip-flop. Again, it is a very simple way of representing. It has a two inputs, J and K, and it has a two outputs. One is a Q and another is a Q dash, complemented output. So with addition to this, you can show the clock signal, clock input, preset input, right? Preset is used to preset the given flip-flop, active low, and another terminal called as a clear terminal in order to clear the contents of flip-flop. Okay, so this is a simple block diagram of JK flip-flop. So what is again here? J and K, these are inputs of flip-flop. These are inputs of flip-flop, right? Q and Q dash, these are output of flip-flop, right? And again, preset and clear, these are the additional terminals. Preset, clear are the control signals, and clock is the input clock. Okay. So let us write the truth table for JK flip-flop. It is similarly written on the basis of SR flip-flop. Okay, so let me write the truth table here. Truth table for JK flip-flop. I am writing this on the left hand side. So input terminals are J, K, okay, and then let us write Q is a present state and Q plus is the next state. Okay, so let us remember that Q is a present state, Q is a present state, and Q plus represents next state. This is a common for all flip-flops. Okay, so again we know that actually there are two input terminals, J and K. So if there are two input terminals, there could be four different possible combinations, right? So 0 0, 0 1, 1 0, and 1 1. Okay, let us say for all these combinations of the input terminal, we want the present state of the flip-flop should remain 0, and for that we want to write what will be the next state. Okay, so let me separate out this two separate cases, when the present state is 0 and when the present state is 1. Okay, again, when the present state becomes 1, there could be four possible ways or four different combinations: 0, 0, 0, 1, 1, 0 and 1, 1. Okay, now let us write the q plus state now for the given jk flip-flop. So when j, k both are 0 and present state is 0, the next state will also become 0 in this particular case. When j is equal to 0, k is equal to 1 with the present state 0, the second state we are explaining, q plus will again remain 0. This is called as a reset condition, because k is equal to 1. K is equal to 1 means it will reset the flip-flop. Okay. Third condition, when j is equal to 1, k is equal to 0 and the present state is 0, the next state will become 1, and this will call as set condition. Set condition, j will become 1. Okay, and please remember, unlike set reset flip-flop, here we will absolutely allow the j and k both terminal to become 1. Okay, and if this is the case, when both are becoming 1 and the present state is 0, the state of the flip-flop will change next time, and when it is 0 it will become 1, and if it is 1 then it will become 0 and it will continue to toggle. Okay, so this particular condition we call it as a toggle case. And please remember, here exclusively I am writing j is equal to k is equal to 1 is allowed or valid state. Okay, now similarly the fifth condition, again with the present state considering to be 1, 0, 0, 0, 1, 1, 0 and 1, 1. Okay, so what happens when the present state is 1, 0, 0, it will remain in the same state when it goes to the next state, right? When k is equal to 1, j is equal to 0, and when you have the present state 1, it will become 0, and this is called as a reset condition. Okay, where k will become 1. Okay, next state is called as a set condition. When present state is 1, j is equal to 1, k is equal to 1, we'll keep it is equal to 1. Output next state. So this is called as a set condition with j is equal to 1. Okay, and when your present output is 1 and when you keep j and k both are equal to 1, okay, so it will start toggling, it will become 0, and if you still keep the terminal both equal to 1, 1, it will toggle between 0, 1, 0, 1 and continuously. This is again a toggle case. Okay, and again let me write here j is equal to k is equal to 1. This condition is allowed, it is perfectly valid. Okay, so this is a truth table for jk flip-flop. Okay, now let us write the excitation table. Excitation table is a sub part of truth table only. Excitation table for jk flip-flop. Okay, so here the output you need to write output is q, and the next state is q plus, right? And for that we need to write what will be the values of j and k. These are the inputs, right? These are the outputs. So first of all you need to write 0, next state is 0, and 0, next state is 1, present state is 1, next state is 0, and present state is 1, and next state is also 1. So for that, what combinations of j and k we should put? Okay, so when present state is 0, next state is also 0, you need to put j is equal to 0, k is a don't care condition. When present state is 0, next state is 1, then essentially you need to make j is equal to 1. This is called as a set condition without considering k condition. Okay. Now when present state is 1 and next state q plus is 0, so that means this is reset condition where j could be anything but k should be 1. And similarly, when present state is 1, next state is also 1. Okay, so j is a don't care condition and k is a 0 condition. Okay, now first of all, let us draw the state diagram. So let me draw here the state diagram of JK flip-flop. State diagram again simple. First of all, you need to draw two circles, each one with different state. Q is equal to 0 and Q is equal to 1. Okay, so that I will show it now here. And then again, by taking the help of truth table, we can draw the transition between two states and vice versa. Okay, so let me draw here. This is the first state. Okay, so this state is, let us call this state as q is equal to 0, and another state right here. Okay, and let us call this state is q is equal to 1. Okay, let us start with the truth table. Now consider this q here. Let me highlight this state you need to consider first. Present state q, right? This column. Now q is equal to 0, that means you are here, right? Now when j is equal to k is equal to 0, next state is again 0. So the next state I will represent here only. This is with q plus when you keep j k equal to 0 0. Okay, now next state is again 0. The second step we are seeing. Now when j is equal to 0, k is equal to 1. So again it will be same, j k 0 1. It will remain in the same state. Okay, now next see the third step in the truth table. When j is equal to 1, k is equal to 1 0, and you are here in the q is equal to 0. So when j is equal to 1, k is equal to 0, the next state will be 1. So that means it will make a transition from q is equal to 0 to q is equal to 1. This we show with a q plus, and for which condition of jk this will happen? This will happen for jk when you make them 1 0. Okay, now again consider you are here at q is equal to 0. When you make j and k both equal to 1, when you make j and k both equal to 1, from 0 state it will go to next state, that is q plus. So this you can show in this way. So next state q plus, and this q plus will be for j is equal to k equal to 1 1. Okay, now let us consider that you are here in q is equal to 1 state as a present state, and when you make j is equal to k is equal to both 0, it will remain in the same state. Okay, so this is the next state. It will come to next state q plus with j is equal to k is equal to both 0. This is shown in condition number 5 here. Now next condition, sixth condition, j k equal to j0 k1. Okay, it is a reset condition. So that means from 1 it will transit to 0 in this way. Okay, from 1 it will transit to 0 q plus. This will happen when j k you make them 0 1. Okay, next state again you are here 1. Okay, seventh condition I am showing, seventh condition here. When you make 1 and 0, it will remain in the next state. So when j is equal to 1 and k is equal to 0, so it will remain in the same state. And when you do the last step number 8, both 1 1, by making sure that you are in a q is equal to 1, what will happen? It will return back to the 0 state. So here you can show this as in this way. When j is equal to k is equal to 1 1, the next state q plus will be q is equal to 0. So this is a simple state transition diagram shown for JK flip-flop. Okay. Now again, by making use of a truth table, let us write equation of the JK flip-flop in terms of 3 variables j, k and q. Okay. Again, for writing this particular truth table, we are going to take the help of truth table, right? Equation. We are going to take the help of truth table to write the equation. Okay. So let us write here. I will zoom out a little bit. Here I will write. Let me come out of this particular highlighting mode. Equation for JK flip-flop. Equation for JK flip-flop. Okay. So how to write equation for JK flip-flop? Actually, for which variable we want to write the equation? We want to write equation for next state. This is called next state, right? In terms of j, k, j input, k input and present state present state is q. So again, 3 variables are there. We need to write a k map for 3 variables, right? So let us draw a k map for 3 variables. And what are those variables? These variables are j, k and present state q. Okay, so let us draw a 3 variable k map. We know the 3 variable k map will have the 8 total boxes, 8 squares, right? Right. This is 1, this is 2, this is 3 and this is 4. And this is the center line. Okay, so total 8 boxes. Okay, so here I will write j, k and here I will write q. So here you can write this as 0 0, right? And 0 1 1 1 and 1 0 and this is 0 1. This you can write this as a q dash also, q dash. This is q. This is j dash, k dash, j dash, k, right? J, k and j, k dash. Okay. Now let us see where the output of next state. Now let me highlight this here, some with the different color. Now we are looking at this. We want to write this. Okay. We want to write the 1 into the k map for the position of q plus. Okay. So q plus position goes 1 4 times. Okay. Where? See here. Step number 3. And step number 4, then step number 5 and step number 7. For these steps, the output q plus will go 1. So only those minterms we are going to include in terms of j, k and q. So first minterm, when j is equal to 1, k is equal to 0 and q is equal to 0. 1 0 0. 1 0 0, here it comes 1. Okay. Then step number 4, see what is the combination of j, k and q? 1 1 0. 1 1 0. Again this is 1. Okay. Then next where it goes, fifth step 0 0 1. 0 0 1 here, right? Fifth step. And then seventh step 1 0 1. So 1 0 and 1. Okay, now we need to form a group. Okay, we need to form a group, and it is very easy to recall this pair you can form and write the expression for this group. Okay, so for this group it is j k q dash and j k dash q dash. Okay, so the k will get cancelled out and this will give the term j q dash, right? Now what about the other terms? Now what you can do is you can fold this k map vertically at the center so that this term will get mapped with this term. Okay, and what this will give the term? This will give j dash k dash, I am writing for this, j dash k dash q, and this term will give you j k dash q, right? J k dash q. So who will get cancelled here? Here j dash will get cancelled with j, and this will give you k dash and q. Therefore, how we can write the equation for the next state? Q plus next state, the equation will be, this equation is j q dash plus k dash q. This is the equation for jk flip-flops next state. Okay, by using k map we form. Okay, so this is all about the jk flip-flop. Okay, sometimes what we do is we connect two jk flip-flops back to back. Okay, so when we connect two jk flip-flop back to back, this we call it as a master slave configuration. Okay, so the first jk flip-flop will act as a master and the second jk flip-flop will act as a slave flip-flop. So what is this particular combination is for? This particular combination is designed whenever two flip-flops are required in a cascaded configuration. Master flip-flop will be triggered on different clock pulse and the slave flip-flop will be triggered on different clock pulse. Okay, so what is the peculiarity of this? Master, whenever it becomes set, then the slave flip-flop will become set, and similarly whenever master becomes reset, the slave flip-flop will again become reset. Okay, now let us go for next type of flip-flop, that is D flip-flop or data flip-flop. Okay, so let us see third. Let me zoom. Third flip-flop, data flip-flop or D flip-flop in short. D flip-flop or data flip-flop. Okay. How it looks like D flip-flop? Let me draw the block diagram. For D flip-flop, it has only one input. Only one input is there. That input we call it as a D input and clock signal. Okay, and we have as usual two outputs, Q and Q dash. These are outputs. Okay, and in between we can write this. This is a simple flip-flop. So the truth table is very simple here. Only one input, only one output. Okay, so here you can write input. Input is D and output we write as a Q plus next state. So when D 0, the same data will come at the output as the next state. So next state will also become 0. Whenever the D input is 1, the next state will become 1. So it is very simple to remember. So whatever you present at the D input, the same will be made output at the next state, that is Q plus. Okay, so simply you even need not to write the K-map reduction to find the equation of next state. Okay, so equation of the next state directly here you can write as Q plus next state is equal to D, right? Because it is D only. So this is a very simple flip-flop. Okay, so this is called as a D flip-flop because whatever you give at the input of D, the same input will come at the output as a next state. Okay, so you need not to write the K-map and reduce the equation because straight away you are going to get the output in terms of D input. Okay, so what you can do is you can convert the JK flip-flop and SR flip-flop into D flip-flop by tying their two terminal with a single one. Okay, so for example, if you take the SR flip-flop, let me show you briefly. Let us say this is a SR flip-flop, S and R. These are the two inputs, S and R, Q and Q bar. Okay, so if you want to convert this into D flip-flop, what we need to do is you give the D input to set input, D input. And what about R input? For R input, you complement the D input and you feed back as a R. The clock signal is as it is here. Okay, so this is SR flip-flop converted to D flip-flop. Okay. Similarly, you can use the same combination for JK flip-flop also, and what you can do is you can connect the J and K terminals with and without D input. For J terminal you give the D input, right? And for the K, what you do is you take the complement of this and fade it as a K and clock signal as it is. Q and Q bar, these are the two outputs. Okay, and this is a flip-flop. So what it shows? JK flip-flop converted to D flip-flop. Okay. Now one more important and last type of flip-flop is remaining, that is a toggle flip-flop. Now let us look at what is a toggle flip-flop. Okay, so the name itself indicates toggle means the flip-flop which has the tendency to change its states from 1 to 0 and 0 to 1. We call it this as a toggling operation. Okay, so next flip-flop, toggle flip-flop. Or in short we call it as a T flip-flop. T flip-flop. Now first of all draw the block diagram. Okay, so how it look like. Toggle flip-flop is essentially a JK flip-flop only. Okay, toggle flip-flop is essentially a JK flip-flop. Yes. Okay, so JK flip-flop, two inputs, right? It's essentially JK flip-flop only, but both when J and K terminals are connected together to 1 as a logic 1, this will get converted into toggle flip-flop, clock as it is. Okay, and the two output Q and Q dash as it is. Okay. When J is equal to K, when you keep both as 1, this will get or this is going to give you the toggle flip-flop, right? Let us write the truth table now. So truth table. Truth table for toggle flip-flop. Okay. So input is T. Okay. And output, there are two outputs. Present output is Q and the next output is Q plus, right? Okay. Now, when the present output is 0 and when your T input is also 0, then the next output will be 0. Okay. This is the first case. Second case, when your present output is 0 and where your T input become 1. So what will happen? It will toggle the present state. Present state is 0. It will toggle, that means it will change the state from 0 to 1. So this is called as a toggle state. Right? Third condition is when your Q output is 1 and when your T input is 0. The present state is 1 and your input is 0. So it will remain in the same state. Next state as the same state. Next state as a same state. Okay. And when your present state is 1 and input of T is also 1. So what will happen then? It will again toggle from the given to next state. Right now it is 1 and it will now become 0. So this is a toggle state. Okay, so this is the truth table. Okay, so how to draw the state diagram? State diagram is simple again. State diagram for T flip-flop. Okay, so again you need to show two distinct states. Okay, Q is equal to 0 and Q is equal to 1, right? Now let us start with the truth table. Now let us say you are at Q is equal to 0 and your T input is 0. When your T input is 0, the next state Q plus is again 0 when your T input is 0, right? Now again you are in a 0 state. Now when your T input becomes 1, your state will change from 0 to 1 and it will make a transition in this way. Next state Q plus will become 1 when you keep T is equal to 1. Now you are here now in state number 1 and the T input is 0. It will remain in the same step. Next step Q plus, it will remain in the same step, same state 1, right, when the T input is 0. Okay, and when you are here at Q is equal to 1 and when you make T is equal to 1, it will again change from Q1 to Q0, Q plus, next state when you make T is equal to 1. So this is a simple state transition diagram. Okay, now I will give you homework to develop an equation for the toggle flip-flop next state Q dash, Q plus in terms of J and in terms of T and Q. Okay, so here next state, right, again you need to take the help of that K-map and so on. Next state Q plus in terms of T and Q, in terms of T and Q. See, so here you can easily look at this particular column. when the next state will become 1. Okay, in these two conditions, step number 2 and step number 3, where the next state is going to become 1. Okay, for that you need not to write any k-map. Okay, you can directly take this combination of 2 and combination of 3 in terms of t and q. Okay, so what you can write then, q plus next state equation. So directly you can write then, so that is t q bar t q dash plus t dash q, or q plus you can write this as t XOR q. So this is equation of toggle flip-flop. Okay, so we saw here the 4 basic types of flip-flops. We started with SR flip-flop, then block diagram, truth table, excitation table, state diagram and equation. The same we did for JK flip-flop, truth table, excitation table, state diagram and equation. And for D flip-flop, it's a simple single input block diagram, then how to convert the SR flip-flop into D flip-flop, JK flip-flop into D flip-flop, and then we went for toggle flip-flop. Okay, so toggle flip-flop is also constructed using a JK flip-flop by tying the both inputs equal to 1, and we saw how to write the truth table, state diagram and equation for toggle flip-flop. Okay, so what we do is, next we will do some exercise to how actually convert one type of a given flip-flop into another type of a flip-flop. Let us do that exercise in the next session. Thank you.